Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 29, 2025, about 3 days ago. The big hook is that this paper weaves Monte Carlo tree search into training for reinforcement learning with verifiable rewards, hitting 62.95% average accuracy while using 5.7 times fewer GPU hours than extended training. The paper is titled DeepSearch, Overcome the Bottleneck of Reinforcement Learning with Verifiable Rewards via Monte Carlo Tree Search. And the implications for model training are quite significant. It tackles training plateaus by systematic exploration, with global frontier selection, entropy-guided supervision, and solution caching replay. On Hugging Face, you can grab DeepSearch 1.5 billion parameter weights, see quick VLLM and transformers examples, read benchmarks and training notes, plus Apache 2.0 license details. Alright, Figure 1 shows the full DeepSearch loop, which integrates tree search into training so exploration becomes broad and targeted. The left panels illustrate global frontier selection, a policy that picks promising leaves using priority and uncertainty, and entropy guidance means the system favors confident positives or the most informative negatives. The bottom strip depicts a replay buffer that caches verified solutions. The right panel presents adaptive training with node-level rewards and iterative set filtering. Well, Figure 1 showed the training loop. Table 1 compares 1.5 billion models on math benchmarks. The headline result is that DeepSearch 1.5 billion reaches about 63% average pass at 1 accuracy, which signals stronger reasoning with less compute. The gains concentrate on challenging sets like AIME and Minerva, so the method improves tough problems rather than only easy ones. The bottom row highlights the new method in bold. The rightmost average column aggregates scores across tasks. So, Table 1 summarized endpoint accuracy. Figure 2 shows how accuracy evolves with compute hours after initial reinforcement learning with verifiable rewards. The blue DeepSearch curve climbs steadily, which signals sustained learning rather than a plateau. The orange depot curve drifts downward, so the baseline loses ground as time passes. Dotted trend lines capture the overall direction, and the markers indicate individual evaluation points. So Figure 2 showed the learning curves. Table 2 compares efficiency head-to-head. The key message is that the method reaches 63% average pass at 1, which signals stronger reasoning at modest cost. DeepSearch reports 62.95% with compute-efficient training that uses 330 GPU hours. Extended training attains about 62%, yet it consumes 1883 GPU hours because it relies on longer runs rather than smarter exploration. So Table 3 tests which search choices matter, using an ablation study that turns components on and off to isolate their effect. The table shows that global frontier selection keeps search depth and entropy stable while cutting wasted work, because it prioritizes promising leaves. The shaded bottom row marks the best trade-off, with similar rewards and fewer iterations per tree. Compared with the vanilla tree search baseline, per tree time drops modestly while maintaining depth. So Table 4 traces how each training component contributes to accuracy. It starts from a vanilla search and adds improved queue updates, fine-grained token scores, and advantages normalization, which steadily raise robustness across math sets. Frontier selection, which picks the most promising leaves in the search tree, delivers the strongest average at about 63%. Gains concentrate on AIME and Minerva because uncertainty guidance reduces wasted exploration. The shaded bottom row marks the recommended recipe, while the rightmost average column aggregates outcomes across tasks. Okay, 2 takeaways stand out. Integrating Monte Carlo tree search into training, not just inference, keeps learning climbing and reaches about 63% accuracy, and smarter exploration delivers that with roughly 6 times fewer GPU hours. The broader implication is clear: scale breadth of search and structured credit, not just training length. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.